Welcome. We are in our last section of this chapter, learning to estimate an unknown population standard deviation. So the parameter sigma, population standard deviation, will be the last parameter that we learn to estimate. So throughout chapter 7, we have been saying that if we do not collect data from our entire population, what can we do to estimate these parameters? And we will go ahead and, as done before, take samples and use those observations to help us estimate our parameters. Now, in order to estimate sigma, we are going to have to introduce a new distribution. It's called the chi-square distribution. So chi is a Greek letter. I'm going to draw a chi over here for you. So a chi looks sort of like that. I'm sorry, let me not put the square on there yet. One more time. Chi. Chi. All right, that's a chi. And you can see a chi right there. But our actual statistic is called chi-square. So chi-square statistic. So rather than looking at the z distribution or the t distribution, we're going to have this new graph called the chi-square distribution. All right, now it differs from the z and the t distributions in that it is not a symmetric shape. It is actually skewed to the right, but like a t distribution, it has an associated degrees of freedom to it, and those degrees of freedom dictate the exact particular chi-square distribution that results. So you can look at these degrees of freedom, they go up, and as the degrees of freedom are going up, you're seeing the shape of that graph change. So the graph actually becomes more symmetric as the degrees of freedom increases. And in fact, the chi-square distribution actually starts to become normal as degrees of freedom increases. All right, but our goal is going to be finding these numbers on the axis, these chi-square values that are needed to construct a confidence interval for the population standard deviation. Now, one other thing to point out about this graph, as opposed to the t or z distributions, is that there are no negative values. So with z and t, we had plus and minus going on, but not for chi-square. So a chi-square graph starts at 0. So smallest possible value of chi-squared is 0. And then, of course, can be larger. So let's learn how to find these numbers, and we're going to do so using table lookups. So we're going to look at a chi-square distribution table. And I'm just going to point out here, I know there's an alpha there, but that value alpha, so the table there, these values that this is saying, they're calling it alpha, these areas are the areas to the right of the chi-square value we're looking for. So chi-square is just a number. These are the areas to the right of the chi-square value we are going to find. So let's jump in with this example of finding these critical chi-square values. So rather than z or t, chi-square, but we'll still have a desired level of confidence. And in order to discuss chi-square, we'll have our sample size here so we can find the associated degrees of freedom. So let's just start with that. Degrees of freedom was n minus 1. So 5 minus 1 in this case, 4 degrees of freedom. So when I get to my table, I know I'll be going to degrees of freedom 4. Okay, and then next, let's just go to the graph here. So when we create the confidence interval, we're still going to try to separate the graph into 3 areas. So that area that's unshaded will be our 80%, 0.80. And then we're going to go through the same process we did when we looked for z alpha over 2. So we're going to find the areas alpha over 2 on each side of that unshaded area. So let's step through alpha. So alpha, remember, was 1 minus our confidence level. So it was the complement of our confidence. And that would be 0.20. So if 80% is unshaded, 20% is the shaded. So those are complements. And then we wanted to know how much was on each side separately. So we took our alpha and divided that by 2. That would be 0.10. And that told me that that shaded area is 0.10, and that shaded area is also 0.10. So you can kind of see here, because of the skewed right distribution, these areas are the same, but this one's sort of taller this way and that one's sort of long that way, but the two areas match. And we can always check that we did this correctly by adding up our 3 areas and making sure we get 1. So we've taken care of that. And then we're going to look for the chi-square values. I'm just going to put a little line there. We're looking for that number. And we're looking for that number, those 2 chi-square values. Let's put a 0 here as a reminder. So there'll be 2 positive numbers here that separate this chi-square distribution into those 3 areas. All right, so we're going to start with this one, and you can see the notation is similar to our z. So chi-square alpha over 2, that subscript is the area to the right of the chi-square value. So we're going to be trying to find chi-square subscript alpha over 2. It can be easier just to call it the chi-square value on the right. And similarly, it can be easier just to call this the chi-square value on the left. But let me just talk about this subscript. So we're looking for this number, and we know the area to the left of it. So I'm just going to add some notation here. So this is the area left of the chi-square value on the left. But in order to use our table, we're going to need the chi-square value and needing to know the area to its right. So we're going to need to know the area to the right of it to use our table. All right, but area left and area right are always complements. And that's why to find that area to the right, we did 1 minus our alpha over 2. Okay, let me just write that answer here then. So 1 minus alpha over 2, that will be 0.90. All right, so chi-square, 1 minus alpha over 2, subscript is because the area to the right of it is 1 minus alpha over 2. That notation gets a little bit annoying, so we can just call this number the chi-square value on the left. All right, you guys, so that is the setup. And then let's go ahead and look at some specifics here. So we want to find chi-square right. We're going to go to the column alpha over 2. To find chi-square right. So let's just do that. So let's come up to our table. I'm going to make a note here. There's 10 columns on the table. So I'm going to just draw a line down the middle of the table. And 0.10 is there. So I can see that the chi-square value answer is 7.779. So let's go ahead and write that down. So chi-square right is 7.779. And I got that by going to that column. So chi-square. Now I could put the subscript on, the 0.10. We can usually just skip that step, it's fine, but the subscript there did tell you what column I went to, and that's 7.779. Okay, and then how can I find chi-square left? Well, now I'm going to have to go to column 1 minus alpha over 2. So our 0.90 column, and let's see what happens there. All right, so that column we find here. And now the reason I drew that line for you down the middle is because the two areas that you look up are always going to be complements. So you can kind of see the numbers come in pairs here. These are complements. If I go out here, 0.95 and 0.05 are complements. So you can kind of see that symmetry in the table. And any value on the right side of the table will be a chi-square right number. Any value on the left side of the table will be a chi-square left number. So there's our chi-square left, 1.064. All right, let me come down and write that guy in. So 1.064. So remember with z-scores, we didn't have to look up two values because with z-scores, they were always plus and minus the same value. Chi-square is just a little bit harder because we have this skewed shape and we've got no negative values. So we're having to look up both of these numbers separately. And let's just finish this then. So chi-square left. So officially that would be chi-square subscript 0.90. But again, we can just say chi-squared right, chi-squared left. And that value came up to be 1.064. Okay, so I know it can look a little confusing, especially the first time. We'll do more examples for sure. But eventually here, we're going to learn to create a confidence interval. And we're going to see these values, chi-square right and chi-square left, in the formula.